Okay, it's 2 minutes after our 6:30 starting time, so let's get started. My name is Ken Fraser. I'll be presenting the material tonight. Just a little bit of background. I don't have any particular, credentials that qualify me here. I'm a member here at Humber Sailing Club. I took coastal navigation 20 years ago, I think, when I actually wrote the exam. And I can't say that it's not something I've used every day in the last 20 years. So I did kind of refresh my memory before I came in here tonight. So hopefully I don't say anything too badly off the mark. I do have my friend Paul here who will correct me if I'm totally heading for a disaster. I hope. Okay, so I guess we'll get started. So I'm not sure how many of you were here last week, a couple of you, I think. We had a slightly different crowd, but last week we went through a lot of the foundational stuff around navigation, the kinds of tools and publications you need, what a chart looks like, the idea of latitude and longitude, dealing with the compass rose and the distinction between true north and magnetic north, how to plot on a chart, how to deal with compass deviation. And I guess finally, we did look at dead reckoning, which is how to estimate your position using your speed and course and time. So that's last week. This week, we're going to look at a little more at the practical side of navigation. So we'll talk about the collision regulations. And I know some of that was covered in a seminar back in November, but we're going to do it again tonight because it's important for navigation, different perspective. So we're going to talk about position determination, how we figure out where we are. We're going to review dead reckoning because it's important to understanding running fixes and look at how we do 2 and 3 bearing fixes. We'll talk a bit about currents, which are not a big deal in Lake Ontario, but elsewhere, definitely, and leeway. And then we'll look at tides and tidal currents and how we deal with that in navigation. So it should keep us busy for the next few hours. So just in terms of housekeeping, if you're online, it would be good if you could keep your mics off. If you do have questions, if you can put them in the chat, that'd be great. If I don't notice your question in the chat, and that's entirely possible, just unmute yourself and yell out. We don't have a big crowd here in the classroom, and actually not a big crowd online either. So if you have questions, yell them out. We'll try and deal with them. Okay, so the collision regulations, we often call them call regs for short. The really long name for it is that the International Regulations for the Prevention of Collisions at Sea. And there's a copy of the, so it's an international treaty. But it's adopted in Canadian law by under the Shipping Act here in Canada. So key definitions, I'll quickly review. A power-driven vessel means any machine, any boat that is powered by machinery. So a sailing vessel, obviously, is not powered by machinery, it's powered by sail. Now, a sailing vessel may have an engine. If it turns that engine on, it's no longer a sailing vessel under the rules, under the collision regulations. It becomes a power-driven vessel. The term underway means that the vessel is not attached to the ground. It's not at anchor, it's not run aground, and it's not tied up at a dock. Making way, somewhat similar notion, but it means that a vessel is moving through the water. So technically you can be underway, but not making way. You could be like dead in the water. So you would still be underway. So a couple other definitions. A fishing vessel is more than somebody who's in a boat with a fishing pole. So a fishing vessel, for the purpose of the collision regulations, means a vessel that is fishing using nets or lines or trawls that restrict maneuverability. So commercial fishing boats may have half a mile of nets dragging behind them, so they're not able to quickly change course. So they have a different status under the rules. Another category is a vessel restricted in her ability to maneuver due to the nature of her work. And this is something like a dredging barge, where they don't have that much maneuverability. They may in fact need a tugboat to come and push them around, so they get a certain status. The next category is a vessel constrained by draft, basically something that's giant, like an ocean liner. So you don't expect them to get out of your way generally. The final category here is not under command, which doesn't mean that there isn't a captain on board. It means that the ship is broken. It means that the vessel has some malfunction so that it cannot maneuver according to what the rules would require. So it's a broken rudder, or the engine's not working, or something like that. And we'll discuss the significance of those definitions in a minute. So under the rules, under the regulations, all vessels must keep a proper lookout by sight and hearing, as well as by all available means appropriate. So that all available means would include things like radar. So it's not in the rules per se, but logically, a person who's assigned to be a lookout should not have other duties, ideally. Obviously have some experience on a boat and trained to in what the regulations are, properly positioned on the boat, so up, above board, and obviously be alert and able to report sightings quickly to the helmsperson or to the master of the ship. The regulations require that all vessels maintain a safe speed, and in considering what a safe speed is, you must consider the state of visibility, how much traffic there is around you, your own vessel and how maneuverable it is, what kind of weather, sea conditions you're in, and how deep the water is compared to how much draft your boat requires. So, if you require 6 feet of draft and you're in 6.5 feet of water, then you should be going kind of like dead slow. There are special rules, regulations regarding what happens in restricted visibility. So they tell you that you must reduce speed, maintain a proper lookout, which you always have to do. You have to display your navigation lights. So reduced visibility either means it's dark, or there's fog, or there's a huge downpour of rain, so it's hard to see. So when you have reduced visibility, you display your nav lights, you use appropriate sound signals. For a power vessel, this is in fog. 1 long blast if you're a power vessel, and a sailing vessel is 1 long and 2 short. And you do that every 2 minutes or so. Okay, there's a couple rules that are directly aimed at avoiding collisions. So under the collision regulations, there's no such thing as right of way. So all vessels have an obligation to avoid collisions, but there's a set of procedures as to who does what. So anytime 2 vessels are approaching each other and there is some possibility of a collision, 1 vessel will be designated the stand-on vessel, and their job is to do nothing, maintain course and speed. The other vessel is the one that's supposed to change course or speed in order to avoid the collision. And we'll look at the specifics of that shortly. So throughout the rules, there's a hierarchy of privilege. Privilege in the sense that the privileged vessel is the stand-on vessel, and a less privileged vessel becomes the give-way vessel. So at the very top of the list, if you're being overtaken, you just can continue on your way, because the person who's trying to overtake you is required to stay clear. The next category is not under command. Obviously, that boat can't maneuver at all. And then you go down the list: restricted maneuverability, constrained by draft, fishing, sailing, but only if you're sailing, actually, not a sailboat under power, and then a power vessel. And those are the normal things you might run into. Aircraft are kind of at the bottom of the list, except for if you're trying to overtake somebody. So if you have a seaplane on the water that's taxiing along and you decide to pass it, well, you are the giveaway vessel. You have to stay out of the way of the aircraft. So in avoiding collisions, your obligation is to follow the rules, or when you're meeting, crossing, or overtaking situations. An important concept is you need to take action in ample time. And the other element is to make whatever alteration you are making obvious to the other vessel. So the shortcut definition, early and obvious. So you don't, making small little adjustments is not obvious to the other vessel, and that will cause confusion. So if you're going to slow down, you slow down a lot. If you're going to change course, you change a lot. And that's to send a signal to the other vessel that, yes, I understand my obligation and I am taking action. So having taken action, you still have to make sure as the situation evolves that your action is sufficient, and possibly you have to take further action. So in a meeting situation, this is where two boats are approaching one another. So if they're power-driven vessels, then if you're going to, meet head on, then it's just like, in a car on a road, each vessel would stay to the right-hand side of the waterway. And so you would pass port side to port side. If you're crossing at a 90-degree or something close to a 90-degree angle, then if you see a vessel on your right-hand side, then you have to give way to it. That vessel on your right hand is the stand-on vessel, and you are the give-way vessel. And obviously, if the vessel coming at you is on your other side, on your port side, then they are the boat that has to stay out of the way. So those are power vessels. This chart, which I guess you can see on your screen if it's not too small. If you're looking at a phone, you probably can't see it. But it gives you the rules. And this chart comes from you can find it in various places, but it's in the Safe Boating Guide that you can download from Transport Canada. And I know we have here in the classroom printouts of this chart as well. So sailing vessels, if your sailing vessels are approaching one another, different rules apply, and it has to do with the wind in your sail. So if you've got the wind over your port tack, so coming over your left-hand side, and so generally your boom is pointing on your right-hand side, then you have to keep clear of boats that are on the other tack. So starboard tack has privilege over port tack. If that doesn't decide the issue, then you go to the next rule, which is that the windward boat keeps clear of the leeward boat. So windward being upwind and leeward being downwind. However, there is a however in the rules, Rule 17B. It says even if you are the stand-on vessel and the other boat is supposed to give way, if they don't, then it's your obligation to take action to avoid the collision. So every skipper is required to avoid collisions. Any questions on any of that? Okay, we're going to talk about position determination, which is, sort of the key element in navigation to understand where you are, so you can then figure out where you want to go from there. So there's various ways of determining where you are on Earth, particularly if you're on a body of water. Some of them are more precise or accurate than others. At the top of the list in terms of precision is the modern global positioning system, or GPS. And if we use that, we call it a GFix when we put it on a chart. Radar is not quite as accurate, but obviously it's, electronic, and it's pretty good. Celestial is listed here next. I think most sailors are never going to do a celestial fix other than for educational purposes. But a sextant is a very precise instrument, even though it was invented 300 or 400 years ago. And if it's used properly, you can get pretty good positioning. Going down to less accurate, we can talk about position fixes using 3 or 2 lines of position. You get down to 1 line of position plus something else. Running fix, we're going to talk about, and then so on down to the very last, least accurate position that we calculate, a deduced position or a dead reckoned position. So we're in fact going to talk about dead reckoning, because while it is the least accurate, it's the simplest to do. And so by doing it, in fact, nonstop, constantly, it gives you the assurance that you are somewhere close to where the dead reckoning position says you should be. So it's a basis for the other navigational procedures that we'll talk about. So the key to understanding dead reckoning is that it's a position that is calculated, it's computed, it uses facts that you already know. Those are facts that are based on past observations. So you know where you started from. You know what heading you're on, or you should know, and you could have written it down. You need to write it down. How fast you were going, you get that information from your knot meter. How long you were moving at that speed, from your watch, timepiece of some sort, cell phone. So those are direct observations using instruments. Variation, that's the difference between magnetic north and true north. You get that off your chart, and deviation is specific to your own boat, and you have to build the deviation table. But if you have that deviation table, then you have that information. And from all of that, you calculate 2 things. You calculate the distance you were moving and how far you went. And then knowing those 2 things and your starting position, you can put down where you're supposed to be based on those calculations. So when we're getting that numbers together, speed we measure in knots, which means nautical miles per hour. Time, for practical purposes, we measured in minutes. We use a 24-hour clock on boat to determine, what time of day it is. So there's always 4 digits. So if you're talking about midnight is 0000, 10 after midnight is 0010, and so on. You come to noon, and that's 1200, and an hour later it'll be 1300, 1300. Distance, we also measure in nautical miles. If you're trying to mark distance on a chart, you have to use the latitude scale, which is the vertical scale on the side of the left or right side of your chart, because that's tied to a fixed position. The number of degrees latitude translates directly into the number of nautical miles. So 1 degree is 60 nautical miles. 1 minute of a degree is 1 nautical mile. So there's a set of formulas that we will use. It's basically one formula. It's very straightforward. It's distance is equal speed time. Speed multiplied by time. Because we're measuring time in minutes, we have to divide by 60 to make the numbers work. And that's one same formula for distance can be rearranged to give you a formula for speed or a formula for time, but it's just the same thing. So I'm looking at, can you tell back here, this chart, if there's a line marked on it? In pencil? Yes. Okay. So that would be a dead reckoning line. So it's a line that starts at the starting point. It points in a certain direction because that's what our ship's compass told us after we adjust it to true. And then we know how much time we were going at a certain speed. And then at the left-hand top of the chart there, the boat changed direction. So that's what that all indicates. And that is an estimated position based on the past motions of the boat. So that's a dead reckoning. So moving on from dead reckoning, any questions? Okay. We're going to talk about taking a fix. So when we talk about dead reckoning, we say it's a position, but we don't say it's a fix. Okay, because there are things that we don't know anything about currents when we do our dead reckoning, and we don't know about leeway, the boat being pushed sideways. So a dead reckon position is not a fix, but these other things that we we'll talk about are fixes because they have a high degree of assurance as to where you are, where you're fixing your position on the earth. So what we're doing to get a position fix is we are using observation and measurement relative to something that's on the land or something that's on the chart that we can identify. So it could be a floating object, could be a buoy. And we're not talking about GPS or any other electronic methods tonight. But yes, you could get latitude and longitude directly off your GPS unit. So position fix, as I mentioned, more accurate than a dead reckon position. And important distinction, it's based on observation that you make at the moment, whereas a dead reckon position is the accumulation of the observations you've made in the past, over some period of time. So because you're doing a position fix at a moment in time, you don't have to worry about current or leeway because it's an instant in time. Once you have that position marked on your chart, then that becomes the starting point for your next DR line. So we can use 2 or more lines of position, or we could read it off the GPS and plot it on the chart. If you're like passing by a buoy, and usually the buoys have numbers on them, so you can identify that buoy on a chart. So then well, that's where I am, where that buoy is. So when you mark up the chart, you would say what kind of position that you have, what kind of fix it is. Is it a two bearing fix, or is it a GPS fix, or is it a running fix? You mark that on the chart. So we're talking about 2 bearing or 3 bearing fixes. So what is a bearing? A bearing is a measure of the direction of an object with respect to the observer. So we express that as a 3-digit number, meaning degrees. So if you are looking straight north, you're looking at something that is straight north from you, then your bearing is 000, because that's due north. If it were due east, then it would be 090. So that's if we're talking about true north, and that's the process that we use for most of our charting. But it is possible to talk about a direction based on your magnetic north. So if you're just looking at the compass, it's going to give you a bearing that is in relationship to magnetic north, and it would have to be converted to true north. So when we talk about magnetic, we mean what a compass, a handheld compass, is telling you when you look at it and it points to the magnetic North Pole. It assumes that the compass is correct and that there's no interference from the boat or from a chunk of metal that's in your pocket, or any other electronic equipment that's generating magnetic fields. When we talk about compass in navigation, we mean the ship's compass, which is physically fixed to the boat. And it often does have some deviation, some distortion caused by the fact that there's probably an engine below it or other things. And to correct for that, we build a deviation table. It's also possible to talk about a relative bearing. So that would be in reference to the vessel itself. So if you're sailing along and you say something, okay, there's another boat that's 15 degrees off the bow. So that's a relative reference. So you're counting from the straight line of the boat, has nothing to do with where the North Pole is or the magnetic North Pole. We don't usually do navigation in that respect, but as I say, for collision avoidance, it would be useful information. So when we're doing a bearing, we have to have something to point at, to look at. So the bearing that the object that you're taking a bearing on has to exist in the real world, but it also has to be located on your chart. So not everything in the real world is on your chart. Most aids to navigation will be on your chart, so buoys and things like that, lighthouses. But most charts will have some reference to obvious physical structures on land. So the CN Tower is a very obvious example. It's on the chart and you can look at it in the real world and you can figure out on the chart where it is. You can also take bearings off of natural structures. So you have a tall hill, you have the end of an island, and things like that you can take a bearing on. Ideally, you're taking bearings on things that are attached to the earth and not something floating, but sometimes you don't have all that choice, so you still have to use the buoy. The buoy is usually where it's supposed to be, but not always. There is a problem if something is too big. So your chart will show the city of Toronto on it, but it's ginormous. So it's not going to be a very useful thing to take a bearing on. So nothing is perfect in the world, and particularly in sailing. And remember, the boat is moving and bouncing up and down on waves. So you're looking at a compass. So you may get some error around what you think is your bearing, and it may be because you misread it across with your eye, or the boat's moving and which makes the compass move. You also have to be aware that your bearing is going to change as the boat moves. So if you're looking sideways at an object that's fairly close, a minute or two, the bearing will change significantly. So one thing you can do to minimize that is if you're taking two bearings, you take the first bearing either ahead or astern, or if it's close to that, and then you take the one that's closer to 90 degrees, because that's the one that's more affected by the movement of the boat forward. So taking multiple readings is a safeguard. If they're fairly close, you can just take the average of them. If you've got two that are close and one that is substantially off, you're better off to discard the wild one. And if they're all in different places, you should probably just start again and do it again, or get a second crew member to do it and try again. So when we talk about a line of position is a bearing that's been converted to a true direction and then plotted on the chart. So pure geometry dictates that your vessel has to be on that line, or it had to be on the line at the moment the bearing was taken. So if you're looking due north and CN Tower, then by definition, the boat is due south of the CN Tower at that moment. So that is the essence of taking lines of position. So when we do lines of position, we take the bearing. It needs to be written down because typically you have to do some calculations with it. It's important to record in your log the measurement framework. Are we looking from a magnetic or compass? Usually we take bearings with a handheld compass, so we would just call that magnetic. The time of the measurement is critical, and the object on which the bearing was taken is also critical. So we would write those things down in the log, and then we would plot the line of position on the chart. So on the chart, we've got the bearing, we've converted it to true, we have plotted it, which is a line that we draw from the charted object out into the lake or the ocean. We write down the time, again, 4 digits, time on top of the line, and we write the direction of the bearing below. It'll be a 3-digit number, 3-digit degrees. So if we have 2 bearings, then we can do a fix, because where they intersect, again, geometry says the boat has to be on line 1 and it also has to be on line 2. So the only point where that both conditions are true is the intersection of the LOPs. And that's where we put a little circle and a dot at the intersection, and we call that a fix. And we would write fix on the chart and the time that the fix was taken. And then we would continue tracking our dead reckoning, and we would start from the dot, regardless of where the previous DR line took us. So this is what it would look like on the chart. So these lines do not represent the movement of the boat. These are bearings. So at 1500, so it's 3 o'clock in the afternoon, we took 2 bearings. So the first bearing on the top part was at 335, true. So they took it using a compass and then put in the variation, and it came to 335. They write that down. And then a minute later, probably, they took the second bearing, but we still use the same time reference for both bearings. And that was at 062 true. And then the intersection is put a circle and indicate that it's a fix taken at 1500. So that's a 2 bearing fix. So 3 bearing, okay, let me deal with this first. So accuracy, your accuracy is affected by the angle of the intersection. So a 90-degree intersection is best. If they're closer to one another, you get more inaccuracy potentially. Obviously, the care and accuracy of taking the bearing on your compass, and some compasses are better than others for this purpose, and the amount of time between the 2 bearings. So theoretically, ideally, you would do them instantaneously, but that's not practical. In the real world, it's going to take you a few seconds to get one, and if ideally you have another crew member that will write down the bearing as you read it off, but you might have to write it down yourself, and then you have to take a second bearing. And then of course it's always possible to make errors in transferring the bearing to the chart. You could make calculation errors, or you could just be sloppy with your ruler. Was there a question? No. Okay, carrying on. So this is a busy chart. So on the left-hand side, upper left, there's the kind of the thing I just showed you, which has got 2 lines crossing. We assume that that's a fix, and we put a circle around it. moving over to the right of that, we've got these, they look like eyeballs or whatever. So we draw a straight line on the chart, but that assumes that everything has been done perfectly. If we allow for some margin of error around that line, then we're going to get this kind of zone effect. And so we've got two zones intersecting. So instead of a dot, we're going to get an area, a little, almost a square. So it might be more realistic to assume that rather than being exactly at that dot, your boat is somewhere around that dot in that shaded area. And again, moving over to the further right, you can see what happens when.
Seems to me.
Yes. Go ahead. Is there a question?
Sorry, it's a mistake.
I'm sorry, say again. No, okay. So if your bearings are not at 90 degrees, then you get this sort of longer area of uncertainty. So the over here, we're looking at 3 bearings. And unless you're very, very lucky, these 3 bearings are not going to coincide at a single point. You're going to get this triangle. And so you would assume that your boat is most likely inside the triangle. Not 100% secure because there's a margin of error on all of these lines. But as a practical matter, that's what we assume, that the boat is in the exact middle of that triangle. And that's where we would put the dot and write our fix. So this is just showing the same things again, the difference between a 2-bearing fix and a 3-bearing fix. So we've already gone through most of this. 3 bearings, basically the same procedure as a 2-bearing. The fact that you have 3 bearings gives you more confidence that the smaller the triangle, the more confidence you would have. And again, you would start your DR, the next DR, from that point. So this is illustrating that situation. We were moving along this line here. This is our DR line. And then we, take this fix. So we do 3 bearings and we wind up with a dot that's in the middle of the triangle. And then we start a new DR line going forward. Oops. I've lost something here. There. So you can see the course is still the same, 270. Our speed is still the same, 5.0, 5.0. We would have, before we took the fix, we would have said we're somewhere on this line by calculating from our direction and speed.
We're not seeing our cursor moving.
Oh, well, I apologize. I've been moving the cursor and you haven't been seeing it online or in the classroom either, right? All right, let me get that. Okay, nothing's moving, right? Okay, I apologize. Okay, I will try and do things without assuming my mouse works. Okay, so if you have the opportunity to do 3 bearings, the ideal is to have them 60 degrees apart rather than 90 degrees because you have 3 of them. And again, the same issues arise. How accurate were your bearings? How much time between the 3 bearings? And how accurate, were you when you're plotting it onto the chart? Okay. The next topic is a running fix. From experience, this is the fix that most people in coastal nav courses have struggled with to some extent. So I'll try and move slowly through it. But if you want me to stop and go over something again, please, yell out. So just to go back for a minute, you'll notice in the position a running fix is down the line. So it's considered less accurate than a two line of position fix, but it's still considered a fix. So it's superior to an estimated position, which we actually don't talk about tonight, or a dead reckon position. So it, in some ways, looks like a two bearing fix, but we use it when we can only find one bearing, useful bearing at a specific time. So we're out in the middle of the lake and we're looking around and we basically see a lot of nothing except for the CN Tower. So we're in the middle of Lake Ontario, you can always see the CN Tower unless it's foggy. So we only have one line of position and that doesn't give you a fix. It just tells you at that moment you're somewhere on that line. So our solution is to use the same object, but we get lines of position at different times. So that can be useful at night when often you don't have a lot of things you can see. You can only see a flashing buoy or a lighthouse. So the process involves collecting two lines, two bearings, and plotting them as line of positions. You do it at different times while the boat's still moving. So you assume the boat's moving. What we're doing here, as you'll see eventually, is that we're using some elements of dead reckoning and some elements of a two bearing fix. So we're mixing the methods from these two ways of determining where you are. So to do that, we have a process that's called advancing a line of position. And what we do is we take the line of position from the first bearing. We look out, we see the CN Tower, we see it's at 45 degrees from, and we make note of that, we put it on the chart. Advancing the line of position has this imaginary process of nailing the line of position to your boat, and then your boat moves and it drags the line of position with you. So I'll show you on pictures here in a minute. So because we keep track of how fast the boat is moving and the direction that we're moving, we have some idea of where the line of position is being dragged to. So I'm going to go through this, I think hopefully slowly enough, but if not, yell out and we'll backtrack a bit. So this is the starting situation. So we are out in the water. We can see this object labeled A, let's call it a lighthouse or call it the CN Tower. And it's 10:30 in the morning. And we can see it 30 degrees off of due north. So we write that down on the chart. 10:30 time and line of position 030 true. The boat itself is headed due east, going 090, and at a speed of 5 knots. Okay, so that line at the bottom is our DR line, our dead reckoning line. So it's our best estimate of where the boat might be, but it is not a fix. So half an hour later, we take another bearing, still at A. We're looking at the lighthouse or the CN Tower, and now our bearing is at 310. So the line of position 310 true, and we put that on the chart as well. Okay, so that's, I think, straightforward. The next part is what some people struggle with, and I did. So we go back to that first line that's labeled 10:30 and 030 on the bottom. And we drag it over by the same distance that we think the boat has moved. So we were going 5 knots for half an hour. So that's 2.5 nautical miles. So we are creating a clone of the object A and moving it over 2.5 miles and keeping the line of position in the same angle as it originally was, but we've moved it over and we put that on the chart and we label that second line, which is the first line moved over. It was taken at 10:30 and then advanced to 1100. So that's written on the line of position. So what the second line that we drew at 1100 and the first line that's been advanced over to 1100 intersect there, and that's our fix. That's our running fix. And we would mark it as such. So an R fix at 1100. And that's where we would start our next DR line from. So any questions? Okay, well, you're all great students. That's just showing that the new DR starts from the fix. We don't continue the previous DR. Okay, so we're going to talk next about currents and leeway. I wonder, maybe we'll take a 5-minute break or something. What time is it in here?
I have a question about the last slide.
Sure.
More like a clarification. So
Certainly.
let's presume we didn't have any drift. No, the previous one. Sorry, back one. If we didn't have any drift, the intersection of the line that was 1100 with 310 and the line 1030 1100 with 030 would have been on the initial charted course. Is that right?
The DR line is marked with those blue arrows. That's, and yeah, conceptually, yes, if there was no sideways drift and everything on your DR was perfect, it's never going to happen, but yes.
Okay, perfect. That was my, yeah, okay.
The reason why the fix is not on the DR line is because of all of those accumulated inaccuracies. Particularly if you're under sail, your speed is not constant.
That's right.
And, unless you've got an amazing helmsperson and, waves and that cooperate, you think you're going, 90 degrees due east, but you could be going, at 88 degrees, 92 degrees. That's why we do fixes from time to time, is because you can never depend on a DR. It accumulates in accuracy. So for the first half an hour or an hour, you might be actually pretty good on the DR. The longer it goes, the more you accumulate in accuracy.
The errors are getting bigger and bigger. That's right.
Yeah.
Thank you.
Okay, so let's take 10 minutes. So I've got 7:20, 7:21. Let's come back at 7:30. Thank you.
Thank you.
Turned off my mic, so hopefully I can turn it back on. I'm sorry?
Working these days?
Oh, yeah.
You're not on mute.
I think I'm muted, but
No, you're not on mute.
I'm not? Okay, well, thank you for telling me. I won't say anything awkward.
So muted and try to say something and I'll let you know if you're on mute or not.
There's too many controls on my screen.
Should be on the lower left.
Well, I've got a different interface than you do, so. Okay, I'll try.
Now you're on mute. Good, good, good.
Moving on screen.
Hmm?
The cursor's moving
Oh.
now.
Oh, because I've moved my cursor over there. When my cursor is over here, when I'm on my screen, it's because I moved the cursor to my screen number 2. Okay, well, that's helpful. Although it means I have to turn around and look at it. I'm back. I hope everybody else is back. We can't actually see who's here. So everybody can yell out present or something.
Okay, present. I
Okay.
can.
Hi, Barbara. Okay. Oh, okay. I've just got a whole bunch of little windows and things that are covering up the list of people. Okay, I guess we're ready to go onward here. Well, hang on a minute. Okay, we're going to talk about currents and leeway, which, so let's start with currents. No surprise, water, we know, is a fluid. So fluids can have a direction and speed of their own. So this is what we call current. It's water flowing from left to right laterally. So if we're talking about lakes and rivers, current is just water flowing downhill. In the ocean, we have either continuous or seasonal currents. There have multiple causes. The salinity of the ocean, which varies across the ocean, the density of the water, the temperature, and then we have the Earth's rotational motion. So all of those things mixed together generate currents. In addition, we have tidal currents, which are caused by the gravitational forces exerted by the sun and the moon. So it's a very busy chart here, but you can see there are currents. These are surface currents. There are deeper currents as well. And they move, north to south. They move from warmer to colder. They move from colder to warmer. The tidal effect generates kind of circular currents in the middle of the ocean, out in the deep sea. Closer to shore, tidal currents are reciprocating. They're back and forth. And we'll talk more about tides later on. When we're talking about current in navigation talk, we may be referring to the specific current at the moment, or we may be talking about the average current in the area. We are going through a pass and it narrows or expands, so the current is going to change from point to point. It's going to change from foot to foot, meter to meter. Currents near the shore are going to be slower generally than currents that are in the middle of the channel. You may have a mixture of currents, so you may have a tide coming in and river going out. So trying to calculate a momentary current could be very tricky, but for navigational purposes, knowing the average current can be all you really need to know. So a current, either we know it because it's marked on a chart or in current tables, or we're going to figure it out graphically. And, that's going to be a bunch of slides later on here. So again, for how we define currents on a chart for navigation purposes, we talk about the set of a current, which is the direction, and the drift. Drift means speed. So set and drift. And typically there's SET is set and DFT is the short form for drift. So when we're talking about the boat is moving through the water and it has a direction, which we call the heading of the boat. And we can calculate the distance traveled by using the boat speed and how long the boat has been moving. So we are, when we do that, we are measuring the speed through the water. We're measuring the motion through the water, but the water can be moving as well. Terminology, particularly on a chart, we use S for speed, we use C for course, which is the heading, the bearing that the boat is moving on. Or we talk about S for speed, the same thing, or CTS, which is course to steer. They kind of mean the same thing, but they're sometimes used, there's nuance. Course is something that has happened in the past. It's the direction that the boat was moving. Course to steer is a planned direction. But I wouldn't, I don't think it's a big deal. You can use one or the other, I believe. Paul, any argument?
Course to steer maybe more affected by leeway or current.
Yeah, they probably can't hear you because you're
Yeah.
muted.
Yeah, pretty similar. Like,
No, Paul's just saying that course to steer can be more affected by the, again, it's a plan as opposed to something that's actually happened. But it's not terminology we need to worry too much about. I don't remember it being a question on the exam. Okay, but what we usually want to know is what is the boat motion over ground, i.e. over the sea bottom? What is the actual movement of the vessel if we chart it, put it on the chart, going from where we started, which is, a fixed position, to a destination, which, we're talking about going from one port to another port. Or we might be trying to describe a vessel which is moving from one position fix to another position fix. So that's boat motion over the ground. And the terminology we use when we're trying to describe that is speed made good or course made good, or sometimes speed over ground and course over ground, to differentiate from our, when we talk about course all by itself, we mean the course as measured from the boat. So what direction is the boat headed in, as opposed to what direction the boat really moved in after you take into account drift or currents or leeway. Okay, so I'm getting repetitive. Of course, the boat has a direction which we call C and a speed we call S. The current has a direction which we call set, and speed we call drift. But for the current, the set is the direction of flow over the ground, and the drift is the rate of that flow. So when we have currents, as the point was made earlier, is the current may push the boat off of the desired course. So navigation problems that we might have to solve at some point. So question, what course to steer to counteract the effect of a known current? So that's in an advanced planning mode. Or it could be that having been out sailing for a couple of hours, you want to know what was the current that affected us. We did our fix, a couple of slides ago, and we found it wasn't where the DR line was. So we want to know what happened and what was the current that affected us. So those are two different problems that we might solve. So we solve these with this basic rule. So we're trying to find boat motion over ground, either the speed or the course. That's equal to the boat motion through the water, and then the motion of the water. You add the two of them together and you get boat motion over ground. So, oops, too much. Okay, so we're going back to high school geometry or high school physics. We're doing vector diagrams to figure this stuff out. So typically, in the simplest situation anyhow, you wind up with a three-sided triangle. Each speed represents, each side of the triangle represents a speed and represents a direction. We always convert speed to distance using time. So if we have, what the speed is, we know what the time is, then we calculate the distance. or vice versa. We know what the distance is, and we know the time, then we work backwards to get the speed. So we're always using the same time period, regardless of what we're trying to get. So we draw the diagram and we essentially measure, we don't calculate what we're looking for, we measure it directly off the diagram. So I'm going to work through a problem more slowly. So in this situation, we have a current that we know what it is. It's, there are current charts, current tables that we can look up, or just maybe local knowledge that, we know that in the St. Clair River, the water moves at a certain speed. So one of the questions is, what course do we want to steer to counteract the effect of a current? So that, you don't, head it over to Niagara in the Lake and you wind up in St. Catharines and then have to, make an adjustment at the end. Or you may want to figure out what's your effective speed traveling over the ground. And a question like, how long is it going to take me to get from Toronto to Niagara on the Lake? So we can solve those kind of problems graphically. And I understand. Let me see if I can get my cursor over here. Okay. Everybody see a cursor moving on screen? Online? Cursor moving?
Yeah.
Okay. And I have to look over my shoulder to do this, but so this picture is okay. We've got a boat here that wants to go from here to there. And it's moving in this direction. So the two arrows on the line indicate that it's a course made good. It's the course that we want to go. It's not necessarily the course that we are traveling or are pointing at. The complication here is that we have this tidal stream and it is moving, the tendency is going to move the boat this way. Ultimately, tidal streams reverse and push the other way. But if the tidal stream continues indefinitely during our course, what's going to happen is the boat will be pushed off course and eventually we'll have to correct and wind up, perhaps beating up wind that we didn't want to. So to figure out the course that we need to steer is we do this kind of graphical work at the bottom here. So I think let's just work through it a little more slowly. So we're doing a planning exercise. So we want to know what is the course to steer and what will be our speed made good, what will be our effective speed. So the known facts that we work with, we know what the starting point is, we know the end point. So we can plot that on the chart. We know what the current set and drift is because we're reading that off of the current tables. And we know what the boat speed through the water is, or where we have an idea of what our boat can manage, either under sail or engine, and we use that in the calculations. So these are the four factors that we're going to use in building this triangle. So just to be very, very precise about what we've got here, we have information about the current. So we know both elements. We know the direction and we know the speed of the current. The boat motion through the water, we know its speed because we know it's our boat and we know what the engine can do or the sails. The course to steer, we don't know. That's what we're trying to figure out. The boat motion over the ground, the speed made good, again, we don't know that. That's what we're trying to figure out. But the course made good, we know what that is. That's a straight line between point A and point B. That's what we're trying to achieve. So I'm going to go through, I just want you to know there's these 8 steps and I'm going to go through them slowly. So let's start. Step 1 and 2 is we pick an hour, a time period, and it's usually an hour for calculation purposes. We're not actually necessarily working on the chart itself. You can get print offs from that are just a compass rose. So it looks like a compass. And it's helpful to figure out, although you could do this on a chart, using the compass rose. So you draw the line between point A and point B, and this is the course you want to follow, the course made good. Again, it has 2 arrows. It's marked as CMG, course made good. Okay, we plot that. We either plot it on a piece of paper, that's marked with a north, south, east, west rows, or we plot it on our chart. Okay,
So I presume that point A is in the center of the rows.
yes.
Okay.
Yeah. Okay, so the current is now, we're marking it at the bottom. So again, it's starting at the point A, the compass rose, and we mark it. So it's going due west here. And we indicate what its set is, which is, the direction and the speed. So the speed, we have the speed per hour. This is why we have it work 1 hour at a time. So in 1 hour, the current is going to pull you whatever it is. If it's going 2 knots, then over here is 2 miles. Okay, you put a little mark on the on this vector at whatever the speed is, the drift. Okay, so now we understand if you do nothing, the current's going to pull you over 2 miles. Okay, so the next here is you're going to go over, and if your boat's measuring, this is you want the speed of your boat. So you put your compass here, sorry. On the latitude scale, if your speed is 5 knots, you would measure off 5 nautical miles on your chart. Okay, so if this was 2 miles, you have to have some kind of scale, then this will be probably not 5, it looks like more like 4, but so you put one point of your compass there, and then you would swing your compass and cut an arc across the other line. So what you're basically saying is that in 1 hour, the current's going to pull you this way, but your boat speed will take you this way, and you'll wind up where you want to be. And that's the essence of the method. So having determined this line here, which is their course to steer, you take that over to your compass rose and figure out what the angle is, and that's your course. And then you measure this line, compare it to your latitude scale, and that will be your speed. Oh, sorry, wrong. You're measuring this line from A to the intersection. That's the speed made good. Okay, does that make kind of sense? Okay, let's try, we'll go through another example. So this time, I'll show you, this is a compass rose that, again, you can find these on the internet. If you have chart 1, by the way, they're, page 12, you can just print off page 12 because it has a compass rose on it. You can use them as worksheets. So again, in this example, we have a current, and we're starting. We also, oops. I apologize. Okay, sorry, we haven't. I think I may have lost a slide here because we've jumped to the course made good in red is 140 degrees. And how do we know that? Here we go. I didn't do these, but I think I've misinterpreted them.
You put your course made good at 140.
Yeah, I mean, it's correct, but how did the order of operations is,
First thing you put on there,
the first thing
put on your course, the course you want to make good, where you're going. where you're planning to go.
oh, yeah, sorry, yeah, it's the red is confusing me. I misread this slide, I'm sorry. Yes, going back, okay, so we know what the course made good, what we want to get, it's 140. We don't know what course we need to travel because of the current. The current we know it's 80 degrees direction and it's moving at 2 knots. Okay, so yes, the slides are correct and I'm the one that's off. So we know our course made good. So we put that on the compass rose. So that's 140 degrees. Then we put the current on. And again, it's we have the set and the drift. And we mark those on here. We mark off 1 hour's worth of travel. So it's moving it at 2 knots. So this distance, this distance from the center to this line here represents 2 knots, 2 miles. And then we do the same thing. We take our compasses, we set them to the speed of the boat. So if the boat's moving at 6 knots, so we would set the compasses to the distance of 6. And we would, put 1 point there, and we would swing the compass here and find the intersection with the course made good line, and then we would label this course and speed. Now we don't actually know what they are until we measure this line. Oops. So basically we take our parallel rulers, take this line and move it over here, and then read it off. So it's somewhere like here. And then we would measure this line. Sorry, we would measure this line, the course made good, to get our speed made good. Okay, I know I probably confused everyone, but any questions? Okay, let's try something else. So in this case, we don't know what the current was. So we're trying to evaluate what was actually happening, having sailed through this part of the ocean or the lake or whatever. So we want to know what was the effective current since the last time we did a position fix. So again, we're going to use a graphical solution. And as a practical matter, we might want to do this exercise so that we know what the current is, so we can do, repeat the exercise we just did to figure out what we're going to do for the rest of our trip. So we wind up with the triangle that looks very similar. But what we're trying to do is figure out the current this time instead of figuring out the vessel. So we have a starting point, and then a while later we have a fix. So on the chart, the graph, we started out, we traveled for a while, we wound up, we did a fix and established that we're here. So this is the course made good. But this is the DR line. We were actually headed in this direction, and we traveled somewhere up here. And DR says we were here, but we actually determined that we were at this location at the fix. So clearly there's a current happening as well. So we've got the DR line there. So we have a DR here, we have a fix. They're at the same point of time after 1 hour or whatever. So the difference between these two represents the current. So we draw that line, we put 3 arrow heads on it because that indicates a current. Then here's the, the kind of stuff. So we know everything about the boat and we know the effective motion over the land. So we don't know the current. So again, step by step. And this is another problem solved, but this is perhaps a little more realistic. So we're going to talk about, we're leaving at 8:10. We were supposed to leave at 8, but we're late. But we're at Half Moon Island, okay, which has a lighthouse. We're on a course due north, 000 true. Speed is 6 knots. 20 minutes later, at 8:30, we alter course. We're now running at 025 true. We're maintaining a speed of 6 knots. At 8:55, which is 45 minutes after we left, we look at our GPS and we, get our lat-long readings and we put them on the chart. So the question is, what is the current that was operating in that area between 8:10 and 8:55? So we're going to ignore leeway for this exercise. Okay, so we start our DR. We put our fix here. So this is the DR, starting at 8:10. We go for a while. We change direction. Okay, this is our DR, saying at 8:55, we should be there, assuming no current. But in fact, our GPS says we're here. So there clearly is some current operation. So what we do is we're determining what is the actual travel over land. So we know we started here, we wound up here, right? So we put in our 2 arrow heads, indicating it's a course made good. And we can calculate, the speed of this by taking the measurement, divide by 60. And then obviously we can measure the direction of this against our compass rose. So now we put in the current. The currents, the effect of the current was to drift and push this point over here. So to determine the direction, the set, we would put our parallel rules on this and move it to wherever the compass rose is. And then to get the drift, we would put our compasses on this, take it over to the latitude scale on the chart and read it off to get the speed. So again, a little more complicated problem, same exercise. So I guess one point I would make is that this course made good is not how the boat actually moved. The boat would have moved something more like the red line. It would have headed out in this direction, but been pushed off, and then it changed course and is continually being pushed off until it winds up there. So the course made good is the net result of everything that's happening. So it's not literally how the boat moved in this situation because it's not a triangle. If it was a triangle, then the boat would have moved along the side of the triangle. But this is perhaps a little more realistic. You don't always do these calculations exactly when you have a triangle. You don't always have the information. Questions?
You double arrow is course over ground, right? You said course made good, but it's the same as course over ground there, right?
So the question is, this is the course Yeah, this is the course over brown, course made good. Yeah, they mean the same thing. Okay, moving on. Okay, the next distortion, I guess we need to consider when we're sailing is leeway. So leeway is the sideways motion of the boat. You're probably most aware of it when you're maneuvering in tight quarters and the boat doesn't go straight, it tends to go, diagonally. Or if you're on a long passage, and again, in the example that we just went through, you thought you were in one place, but a GPS fix said you were sideways to that. The cause is wind and waves, which are, also caused by wind. But sometimes the wind and the waves will be operating in different directions. So leeway can vary depending on lots of things. The kind of boat, the design of the boat, the condition of the boat, how much barnacles you have on your boat, the windage, what sails you have up, or just, the shape of the boat, how high it sits in the water, the configuration of your keel, full keel, dagger keel. The relationship of the direction of the wind and waves versus the course being steered. So are the waves hitting you sideways, on the stern, on the bow? Are you carrying too little or too much sail? What point of sail are you on? Are you reaching, or are you running downwind? Helmsman, all these things can affect how much leeway is happening. I'm not sure how useful this diagram actually is, but it's trying to indicate that the red line here is the actual course where your boat is heading in this direction, but you're being pushed, the leeway, the effect of the wind and waves is pushing you that way. So what you're actually, which is, this is the effect of winds and waves. So this is the direction you're actually kind of moving. So even, I would rather this red line go over here and then being pushed down, but leeway, unlike the currents where we can do fairly, precise calculations, leeway is more of an estimate. And these numbers were just given here to me. But you're going to get more leeway when you're in close haul because of the, the way the wind interacts with the sails and the keel, and less on a beam reach. You can estimate what the leeway is. You can look back behind your boat and you'll see your wake through the water. And, you look at the angle of the wake. Is the wake dead behind you, in which case there's no leeway, but typically it's off to one side. And if you take a bearing, take your compass, handheld compass, and point directly behind you and then along the wake, that will give you an estimate of your leeway. Or you could, tow a line behind the boat and again measure the bearing of that line versus straight back. So that's your leeway. And when you have that estimate, what you need to do is adjust your compass course to correct for it. So again, another diagram. This is the course you're pointing at. You're following on your compass, but you've got wind. So what's going to happen is you're going to wind up, in this case, 12 degrees off of where you think you want to go. So the correction is you just go 12 degrees the other way. So this slide is saying if the waves are from the port side, you subtract leeway. If the winds are from the starboard side, you add it. From my perspective, it's easy to remember you're always heading upwind. The adjustment is always upwind because that's where the drift is coming from. So you can either make a direct, you can do through your calculations and come up with a course of 090, and your leeway is 10 degrees. So you can subtract 10 degrees from 90, and that comes out to 80, and just do that. That's the easiest and most straightforward. Probably the more technically correct process is to convert your true course back to magnetic, and then adjust for leeway, and then reapply deviation, because the deviation might have changed when you changed your course. I think we're into fine tuning. If you're crossing the Atlantic Ocean, that's probably important. It's probably not that important if you're going from here to Niagara-on-the-Lake. But, be aware that there is technically, it's not, a direct correction to the compass course is not giving you the proper deviation. Lots of times we don't have a proper deviation table, though, in reality. Any questions on that last part?
No.
Okay. So we're going to talk about tides and currents, tidal currents. And this is the area that I have the least. I think I've sailed once in tidal waters. And I didn't run aground, but I did mess up on the tidal current when I was coming back into dock. So we've talked about tides and currents. We're going to talk about tidal currents. We're going to talk, they're kind of different in some ways than the currents we've been talking about, although the math is the same. Okay, and why do we need to understand them, and where do we get the information? So tides, I think we mentioned tides are caused by gravitational forces, mostly by the moon, but also by the sun. Obviously the sun and the moon move, the relative motion of the sun and the moon with respect to the earth are different, because we see the sun go around up and down every day, and the moon goes much more slowly. But sometimes the sun and the moon are pulling in the same direction. So you get high tides in that situation, or sometimes they are pulling at 90 degrees, or they're pulling in opposite directions. So we either get spring tides, and the spring doesn't mean the season spring, it means, think about springing up. So when the moon and sun are pulling in the same direction or in the opposite directions, I don't know how well you can see this kind of fuzzy diagram on the slide, but basically, when the sun and the moon are on opposite sides of the earth, you get high tides, and when they are 90 degrees, you get lower tides. You still get up and down in every day, but the maximum minimums are more restrained when the earth and the moon are at 90 degrees. So when we talk about tides and their motion, they have two directions that we think about. Tides have a height, so up and down, vertical motion. They also have a left to right or right to left, north to south kind of motion, horizontal motion, which we measure as a tidal current. So when we talk about a rising tide, tides are going up, then we call that a flood current. The water is flooding in, and when the tidal height is going down, then the water is going out, it's ebbing out is the terminology. So tides have different cycles in different parts of the world. So one cycle is called diurnal, which means once a day. So once a day you have a high tide and a low tide. So every day, every lunar day technically. And this is common in the Gulf of Mexico. So you have one tide. We also have a cycle called semi-diurnal, which means we have too high and too low tides, more or less in the same magnitude every day. And that's typical of the east coast of North America. And finally, we have what's called a mixed semi-diurnal tidal cycle. And that's what we call it when we have too high and too low tides, but they're quite different. The too high are different and the too low are different. So this is what's illustrated here is this is high tide, this is high tide, this is low, this is low. So there's a big difference between here and here, a pretty small, modest difference between this one and this one. And the West Coast, North America has tides like this, my understanding. So to get information on the tides, we have tables available from Transport Canada. And I'm sorry, you're not going to write it down, but the link is no longer effective. So if you actually want to look at this stuff, the link is actually very simple. It's charts.ca. Charts.gcca, I think, Government of Canada. So they have all these charts. They're free to download. So you can get them off the printed charts. There is a kind of an app on the charts.ca, so you can get like the tidal information for one day. The printed tables give you information for the entire year. There are also almanacs with this information. Some electronic gear have apps that give you tidal prediction, and people who live in the neighborhood kind of know this stuff without even thinking about, it's whether it's high tide today at noon or whatever.
My local radio stations always put it out too.
Okay, Paul mentions that local radio stations will predict the tide, give you tidal information. So that's the height. Similar tables also, sources give you the direction and the speed of the tidal water flows. Depending on why you need the information, you might need the height information, or you might need the speed of the current. So if you're anchoring, you want to know what the height is, or if you're docking. If you're traveling from point A to point B, you may be more interested in what the direction and speed of the tidal currents. Okay, so let me just skip. I want to show you this next slide first. So this is what the tide tables look like. So these have been around for decades, in this same format. These are the same format they used 20 years ago when I took my course. You can see there's 3 months of data on this one page. There's information for every day of every month of the year. So these are 2012, which is when this slide was created. And the 4 tides per day. So over in this corner here, it says that July 1st, 2012, there was a high tide at 5:22. Then there was low tide at 11:42. There was a high tide at 17:32. These are the heights, or feet, meters. This one, of course, happened after midnight, so the next tide is here. And then you can work your way back down week by week and month by month through the year. So let's go back for a minute. So there's a lot of information. The tides are very complex. The mathematics is complex, much beyond my math. Amazingly, 200 years ago or 150 years ago, they used to do tidal calculations using a mechanical calculator. It was a complicated machines with wheels and things, and you would crank it and it would generate tidal predictions. So partially the problem, there's 2 issues with these are predictions, based on the past, and they do kind of repeat. But we don't have enough tidal stations to gather enough information. And if you printed it all off, it would be a huge book. So the way it works is the tide tables have two sections. There's what's called the primary or reference port being, a place to dock. And they predict that's what we're looking at here on this slide. It was day by day, such and such, okay? So those are the primary reference port information. And then the secondary ports, which are usually less important places that are up the coast or down the coast a bit, are called secondary ports. And they don't get the full detail that I just showed you, but what they get is the difference in time by which a tidal event will precede or follow the reference port, and the difference in height. So what you're supposed to do is if you're going into a reference port, it's fine. You read it directly off of the tables. If you're going into a secondary port, then you have to go to the reference port, get that information, and then add or subtract adjustments for the secondary port. So that's, I'll give you more. So this is our standard port, the primary port. By the way, tide tables are always on standard time. So this is in the summer, but all these times are standard time. So you have to make that adjustment when you're working with these tables. This is an image from the website, again, tides.ca, tides.gc.ca. You plug in the date and it will give you just the information for that day. Okay, so the secondary ports are sort of compressed tables. They don't have as much detail because they're basically saying you take the reference port and then you add or subtract the time difference and the height difference. So the main port would say something like, okay, we're going to have 6 feet of tide at 5 o'clock. And then sort of a few miles down the coast, 10 minutes later, the tide's going to peak at 5:10, but it's not going to be as high because it's kind of washing out. Typically the tides, spread out and weaken. Or they may, if the Bay of Fundy, they actually increase as you go further down the Bay of Fundy and everything piles up. So you start with the reference port, you make your adjustments. So the example here, sorry, let me go back for a minute. So we're looking at Port Atkinson is the reference port. So it's the more important port. And it has a page to itself in the tide tables, day by day, tide by tide, year by year. Okay. Then the secondary ports are listed in a different table, table 3 here. So you see, this is Port Atkinson, which is the reference port. So if you want to go into one of these, Porpoise Bay or Storm Bay, the first thing you have to do is go back and get the data from Point Atkinson, and then add these adjustments. So the time adjustment is 10, Storm Bay is 2 hours and 39 minutes later. The mean tide is 8 feet lower. And that's for the mean tide. For a large tide, it's different. Anyhow, it's complicated. And there's a lot of, writing things down.
I will say that once
you're there and have done it once or twice.
I can see it going up and down.
Yeah. Yes, Paul was saying, once you've done it, once you're there in location, and instead of, when you're actually there, you're not looking at 500 numbers on a page, you're looking at 2 numbers on a page because you know where you are and what you have to do. So the one time I was out in Vancouver, I was going up to Lions Bay or somewhere. Anyhow, so I was told by my friend out there, you got to go the long way around because the time you plan to go there, the tide over Deadman's Shoal or something is only going to be 6 feet, or something like that. So you shouldn't do that. So I went around the long way, but the next morning the tides were different, and I used the tide tables and I calculated what the amount of water should be. And, I said, okay, do I dare this or not? But I did, and I was watching the depth meter. Okay, it's 50 feet, it's 40 feet, it's 30 feet, it's 20 feet. And then I cross over, it's 9 feet, which is what I predicted or whatever. But yeah, so once you've done it once or twice, you get some comfort with the method, but it is hard to explain and hard to understand until you've done that. Okay, tidal currents. We've talked about the height. So this is kind of when you're close to land in shallow water, you want to know what the height of the water is. So all these numbers, where it says, sorry, let me go back just to the tidal table. So it says here 5.6 feet. So you take that number and you add it to what the chart says is the depth at a particular point. So these tides are measured from chart datum. So this is extra water on top of chart datum. Sometimes they can be negative. I don't see anything here, but technically a tide could be negative. They try not to have that happen. They try to set chart datum so that it's pretty much the lowest it ever gets. Okay, tidal currents are the movement of the water as it comes in and out of ports. So either the tide is rising, in which case you have a flood current, or it's dropping, and it's an ebb current. And like any current, whether it's in a river or whatever, tidal currents have a speed and a direction. Unlike a river, they change constantly. Rivers are fairly constant. So again, we talk about tidal currents. They have a set, which is the direction, and they have a drift. But they do go back and forth. So you have to be careful as to whether they are flood current or an ebb current. The flood currents are designated as plus signs, or sometimes as these backslashes, and the ebb current are negatives. So when we talk about slack water, the slack water is the point during the day when the direction changes. So the tide flows in, and then it kind of stops for a minute, and then it flows out. And they're highly predictable, these slack waters, although weather conditions can affect them. So if there's a heavy storm, that can change the timing of tides to some extent. The maximum rate is the rate is not constant. It speeds up and then it slows down and then it reverses and goes out. So the tide tables, the tidal current tables will tell you what the maximum rate is and the time of the highest rate between turns. And you can use that to do some of the current calculations that we discussed earlier this evening. So you look up these currents tables and they tell you that you're going to have a 2-knot current during the time that you're traveling through a certain part of the lake, then you have to calculate that. Yeah, so the current tables give you all this information. They, just like the tidal depths, they give you a listing for a reference port and a separate listing for differences at the secondary ports. Again, these are predictions based on past measurements and always in standard time. So I was reading the actual tables today. They use about 12 months of data, so it's not like long-term historical patterns. They use about 12 months of data for the primary ports and sometimes less than a month for the secondary ports. So again, these are current tables, they look a lot like the tidal tables, the tide tables, but we're not getting heights of tide, we're getting speeds. And so this is the maximum speed at this time. This time is, there's two times here. This time, 0210, 2:10 in the morning is the time of slack water. So the tide is about to turn. And then, come on, cursor. So about 3 hours later, the maximum current is achieved, 4.3 knots. So you don't want to be sailing against that if you can help it. And then a few hours later, 9 o'clock, the water kind of slows down and turns. So you got slack water, no movement. And then you go in reverse. So the -4 means that the tide's running out. So plus tides are going, the tide's going down. So you get minus. And again, you can see plus, minus, plus, minus, plus, minus all the way. And so that's the information from the the current tables. Yeah. And you would use them in conjunction with the tidal tables if you are navigating in a place like Halifax or Vancouver. Or tides in the Gulf of Mexico are not very significant. And there's Mediterranean too. Tides are quite minimal in the Mediterranean. So this is just the same notion. Again, we've got reference and secondary stations. They call them stations as opposed to ports. Because I think some of this information is taken from buoys that are anchored out in current areas rather than, the tidal heights will be like, inside a harbor. Anyhow, don't quote me on that, I'm guessing. So that's, again, secondary ports, same concept as, oops, what happened here? Okay, I may skip this. This is just an example. Well, sure, let's walk through it. We've got a reference station. We take the information from the reference station, and then we take the differences at the secondary. So there's difference in time, and there's a difference in the maximum rates, which are expressed as percentages. So the calculations look something like this. We've got here's the turns. This is the reference station, and then you add the adjustments. So the slack water, is an hour and 40 minutes later, and then the maximum flood is higher. The time, sorry, this is time. So you got these two times, and then the rate of flow. The reference port is 2.2, but you only have 20% of the flow at this secondary port, or 25% when you're going in the other direction. So that's again how you get current estimates at the secondary stations. So it's a two-step process. Any questions? Anybody got any ambitions to sail in tidal waters?
Oh, one quick, if you live in tidal areas like Vancouver, and you have a lot of heavy.
Put your mic on.
Oh.
No, just on mute.
I'm just going to say, if you live in a place like Vancouver where you have a lot of loading a boat with heavy equipment and bags and whatnot, it's best to wait for the tide to be high because an 18-foot tide means you've got a very steep ramp to go up and down to load your boat. Some of those loading ramps on floating docks can tip down a 30-degree angle. It's trying to lug water and luggage up there. Okay.
Interference going on here, so there are better views.
You're on mute.
Okay, I was trying to suppress the interference here. Yeah, Paul makes the point that if you're in high tidal areas that you want to launch your boat
Getting up and down the ramps is ridiculous sometimes.
Yes, so there's ramps that, the docks are floating or whatever. So at low tide, you're going down this steep ramp, or at high tide, you're climbing up ramps. So you want to choose your time for when the ramp is flat to get onto your dock or onto your boat. Is that the point?
Yeah.
Yeah.
Wheelchair or whatever.
Yes.
Maybe equipment.
Yes, if you're pushing a cart full of provisions, you would prefer not to have a 45-degree slope on your ramp. Okay, good point.
Another question, are you going to cover the tidal diamonds?
No.
Okay.
But yes, there are, I think you're referring, I have to remember what this is. There are various methods to estimate tidal flows and tidal heights in between the maximum and minimums that are given in the tables. And I think that's the tidal.
Tidal diamonds is you can estimate the set and drift for the currents at certain points on let's say.
Oh yes, that's in the current almanacs, and some charts have that information. Yes.
Yeah. Okay.
I'd forgotten that, but yes, I do remember that from the that.
Yeah, they're used on the St. Lawrence River.
Yes. Yeah, you'll see them on.
Currents are kind of all over the place.
Yeah.
The
Yes.
sets. Mostly.
Yeah. Okay. Yeah, we don't have them in Lake Ontario. So I did look it up. I think the tidal differences in Lake Ontario are about 2 inches. So we don't pay attention to tides, and there are no tide tables for on Lake Ontario. Okay, we're going to talk about how you plan for a voyage and navigational aspects of that. And okay, so if the navigator is a different person than the skipper, both of those people have responsibilities. You're doing planning so you can establish expectations and the timing, like when do you need to leave, and so forth. When we arrive, you're trying to make sure that your passage is going to be done safely and comfortably, and is appropriate to the skills and aspirations of the vessel and the crew. So there's kind of 2 levels. There's a high level view of the thing, and then there's some details that you have to think about as well. So step 1 is making sure you have the charts and publications that you're going to need along the way. So you need small scale charts, which are charts of big areas, to get an overall plan. For detailed navigation, you need large scale charts. So a large scale chart shows a small area. You probably, if you're going to sail at night, and even if not, you should have lights, buoys, and fog signals at list, a publication, sailing directions for the areas that you're sailing in or going to. If you're in tidal waters, you'll certainly want tide and current tables. Cruising guides are not a government issued navigation material, but they can be very useful to know what happens when you arrive at a port, the mechanics of getting in, what marinas are there, what facilities are there, where the liquor store is, where the grocery store is, and those kind of essentials. Charts So this is a small scale chart, and it's small scale because it's got a big number on the denominator, 1 to 400,000 scale. And this is a example here. This is all of Lake Erie. And, so you see the entire lake. So you get the big picture, but you don't get a whole lot of detail on this chart. There's a medium scale. So that'll get you, close to where you want to go. But you'll need a large scale chart to get you into the harbor, with all of the specific detail that you would want, the, depths of the water, where the buoys are inside, private buoys, warning signs, and so forth. So you need charts. And they could be on paper, or obviously they could be on electronic chart plotters these days. Other elements of an overall high-level plan is like, what's your route? Around here, Lake Ontario, Lake Erie, we got large bodies of wide open water, but other situations where up in Georgian Bay, where I have a cottage, there's islands all over the place. There are rocks that you can't see all over the place. So you do need to make sure you have a safe route. What's the minimum distance you want to travel every day, and can you achieve that? Look at the weather. What, if you're going out for 3 days, what's the weather going to be for 3 days? Wind direction and velocity will determine whether you're sailing, upwind or downwind, or whether you can get to where you're going, I suppose. Temperature, is it going to rain? Think about what would happen if things turn bad. If your fog rolls in, if the wind picks up, is there a port that you can get into? Have a contingency plan. If there's navigational hazards, you have to have some sense of where they are and how you're going to avoid them. Understand your equipment, understand your crew, determine what navigational methods are you going to use. Are you going to do traditional paper nav? Are you going to rely on electronics? If you're going to rely on electronics, what's your backup if they don't work or you lose batteries? Understand your current and projected sea state, wave height, and period, which the marine forecast gives you. More detailed information. If you're in tidal waters, obviously you want to know what your tides are. If you're going to be going under bridges or power lines, you better know how tall your mast is and have adequate clearance. Depending on where you're traveling, the timing of your departure or arrivals may affect how easy it is to get in and out of certain harbors. You think about where navigational aids are, lighthouses, buoys. Think about weather conditions that could make things particularly hazardous. If there's a known hazard and you need to identify certain buoys to navigate safely, you want to know that in advance. So building your plan, you start with the big picture, which is the small scale map. Establish your general route. Is there any place along there that you have to be there at a certain time? Again, thinking about tidal waters. If you have a strong tidal flow against you, you don't want to arrive at that time. So you want to plan your voyage so you arrive when the tidal currents are favorable to you. Marinas might not be accessible at a certain time. They might close if you're too late. Weather conditions. Not Mars is the notice to mariners. So you should have up-to-date charts. You get that information from the NOTMAR service. Figure out when you want to arrive at destinations and work backwards to when you have to leave and what kind of speed you have to make. Because you might have to decide halfway through that the sails come down and the engine goes on in order to make your destination at a reasonable time. Anyhow, and then finally, you need to look at your large scale maps to look for danger that doesn't show up on the big picture maps. So you would plot, if you're traveling across Lake Ontario, you would take the chart for Lake Ontario or Western Lake Ontario and, plot your course across that. And that will get you, near Niagara Lake or St. Catharines or wherever you're going. Figure out your critical arrival times and, calculate backwards. And then transfer, if you're going to arrive at, Niagara and the Lake at a certain point, and you're going to be, quarter mile off I think there's a lighthouse there. So you go to your small scale map and you transfer your position there based on latitude and longitude. Figure out bearings to features that are common on both charts to establish, where you are and your direction. Pilotage plans, we'll talk about pilotage in a few slides. In fact, this one. So pilotage, it's part of navigation, but is sometimes, carved out and talked about separately. Pilotage is the process of navigating when you're near shore and where you have, lots of visual references to help you along into the coast. Typically, buoys or breakwaters and things like that. When you're in that kind of close situation, when you're arriving and you're navigating through channels into marinas or whatever, as a navigator, you want to be on deck where you can see things, and ideally not having to go downstairs to check your chart. So you should build a pilotage plan, piece of paper, write it down, make a list of the various landmarks you're going to be passing, the buoys, whether they're left-hand or right-hand buoys, write down the chart numbers for those buoys so you know that you're on course. Some sense of the distance between them and how long you expect to travel from point, B to C to D. You can do back bearings which is sort of the bearing if you would look backwards instead of looking forwards to confirm that you're on your planned track. There may be speed limits or local restrictions that you should know about. You get them from sailing directions, potentially from the chart sometimes. Sometimes it's critical to turn at certain points, and you should want to know there may be shallow water, immediately on the other side of a buoy. The depth, often channels channels into harbors are dredged, and they may be fine as long as you're exactly inside the buoys. But go 2 feet on the other side of the buoy and you're in 3 feet of water. So you don't want that. You need to know what your critical path is. So lots of things to think about, for pilotage. So there's a couple ways you can, document that. You can take a chart, or some kind of photocopy of a chart, and draw in the things you want to remember, or you can just take a blank piece of paper and do a sketch. Just noting the important things that you want to, which buoys you want to see, where you want to turn, and so forth. Okay, I think that's it for our presentation. Is there any questions on this last part or any part?
No.
Okay, well, let me give you the commercial. So if you're keen to learn more about navigation, you can take proper courses from Humber here, Humber Bay. We have an upcoming Sail Canada course, Intermediate Coastal Navigation, coming next month. I think there's spaces. There's also a course on celestial navigation. And although it's probably not going to be something you want to use, I think it's fascinating kind of subject. and I haven't, so it's there. We teach that. We also have additional club seminars coming up. Next, I think these are all correct, Paul? Yep, okay. Next week is boat design, and then introduction to racing, boat systems, risk management, weather, which is always a great one, and intro to sail trim. And again, it's intro. We have a whole course as well on that here at the school. So again, these courses are all taught here at Humber Bay Sailing Center. They're unlike the seminar tonight. You're going to get certified, competent instructors for all these courses. And if you're interested, you can go on the website or you can phone the office here. So I think that's it. If there's no questions.
Well, I have a question.
Sure.
Are you guys making available the recorded course?
Sorry,
Like
these
this-
slides. So are we making available these slides?
No, this course, this seminar.
This seminar, no. There's various copyright issues. We didn't create these slides.
Okay.
So we're using them under license.
Okay.
But we're not licensed to just further distribute them.
Okay,
Yeah.
that's it. No further questions from me.
Okay. Well, thank you everyone for coming. I hope it was of some interest and some value to you. You know, it's always good not to hit rocks when you're in your own boat or in my boat, if you're sailing in my boat.
Yeah, thanks a lot. I really appreciate it.
Okay, thank you again.
Thank you.
Bye.